The last bit of impulse that we're going to talk about relates to graphs. The impulse graphs that we're going to look at are actually graphs that are force versus time graphs. Force on the y-axis and time on the x-axis. In fact, every time you see one of these graphs, a force versus time graph, I want you to think impulse. I want you to think impulse. In fact, more specifically, I want you to think 3 words. I want you to think area equals impulse. Whenever you see F versus G, whatever the shape it is, I don't care whether it looks like this, I don't care whether it looks like this, I don't care whether it looks like this. Think area equals impulse. You will, whenever you have a graph and you have to do a calculation with it, there's times when you see a graph and you just have to interpret something, but whenever you have to do a calculation with it, every single time you'll need to know that area equals impulse. Now, sometimes the area is above the time axis or above the x-axis. In that case, we're going to make it a positive value for impulse. If it's below the x-axis, we're going to make it a negative value. So if your graph happened to look like this area up here would be positive, and this area down here would be negative. We'd add those two together and we get a total impulse or a total change in momentum. Occasionally, you may have to go a step further. It's not enough to just do area equals impulse. You'll still do that, but you'll have to go beyond area equals impulse. Once you have the area, you may have to use this equation to find the change in velocity. So you see this graph right up here. You've calculated the area. That represents the impulse. You're given the mass in the question, and then you rearrange that to solve for the change in velocity of the object. Even if you're looking for the change in velocity, though, the first thing you're thinking is still 3 words. What are they? Area equals impulse. Every single time. Every single time the problem involves math, area equals impulse. Best way we can illustrate this is with an example, page 462. It says a golfer, Alex just asked a question about golfing earlier. Golfer hits a long drive sending a 45.9 gram golf ball due east. And this graph shows the net force as a function of time for the collision between the golf club and the golf ball. Forget about the question here, okay? As soon as you see this question, before you even really read anything, you should think 3 words. What are those 3 words? Tony, what are they? Area equals impulse. Good. We see a graph. It's force versus time. Okay, area equals impulse. Now, even, again, before we read the question, potentially, you probably should circle that. Milliseconds. Sometimes we see newtons and kilonewtons or millinewtons or something like that. Okay, draw attention to the fact that those aren't standard units. Okay, once you've recognized that it's area equals impulse, you've identified those little things like funny units that we got to convert. Now let's look at the question. Question says, what's the impulse provided to the ball? All right, good. I got to find impulse. I know area equals impulse. Seems easy. The second question, a little bit harder. What's the velocity of the ball at the moment the golf club and the ball separate? A little bit harder, but I think we can still do that. Okay, let's do A. What am I going to do for A? Listen, you don't even have to think about this, do you? We've already identified what we have to do for A without even knowing what A was. Bryce, what are we going to do for A? Yeah, find the area of it. The triangle, right? So it's 1/2 base times height. It's 1/2 of a base, which is, oh, be careful on this. Goes from 0.1 to 1.1. Here, the base is 1 millisecond. Good. That's 1 times 10 to the minus 3 seconds. Okay, I might have forgot to put that 10 to the minus 3 in there. If I hadn't circled milliseconds, I might have just called that 1. The height is 5,000. I think when you do that, I think it works out to be 2.5. And the units could be, you could go kilograms, meters per second, same as it is for momentum. Or you could say base times height, Newton seconds, that works as well. Either one of those work. Is that easy? Easy, hard? Boy, if you see that on your quiz tomorrow, you should ace that, I think, right? Just remember, if it's below the x-axis, make it negative. If there's a milliseconds in there, convert it. Otherwise, I think it's pretty straightforward. All right, B, what's the velocity of the ball the moment the golf club and ball separate? Well, to find the velocity, we're going to say delta P is equal to m times delta V. Hey, question for you. I'm using m times delta V here. Why could I not use anywhere in this problem this? Why could I not use F times T here? Seems like it should be valid, right? Technically, it is valid. But why can't I use it? What does delta T mean? The time interval. What does F mean? Force. What force? Sorry. The net force? What's the net force here? It's changing, right? It's changing. Technically, if you could find the average net force there, that equation could be valid. It's easier just to find the area. They get you the same thing, and it's easier to get the area. But there's no problem with this equation at all, because mass is mass, it's not changing, and delta V is from start to finish. You don't have to find an average or a constant value or anything. So we're good to go on this. Look, we got the impulse already, it's 2.5. We got the mass, it's, probably should have circled that as well, right? 0.045. 0.0459 kilograms times delta V. Oh, wait. Do I have the right impulse? Let me trace this graph over, and I want you to say stop, yell, stop. And I mean, when I say yell, stop, yell it. Yell stop when the ball and the club separate. Okay, I'm going to trace it over with a red pen here, and I want you to yell stop when the ball and the club separate on this graph. Anyone yet? Position A or B does it separate? Who says A? Who says B? B's right. B's right. Let's think about this. Golf club hits golf ball. Okay, golf ball compresses. Alex, we were talking there when you had asked that question earlier. Golf ball compresses to not much more than half the size that of its normal size. Okay, it gets really, really squished. It gets wider, but it gets squished, right? Not as thick. About half the thickness. As it squishes more and more and more, it's kind of like a spring, like Hooke's law, right? Remember that from Physics 20? As the spring squishes more and more and more, the force gets bigger and bigger and bigger. But then at some point, when you're hitting the golf ball, the force is maximized, right? And then what happens? The force on the ball gets smaller as the ball starts going back to its normal size, to its regular size. So the force decreases, but the club is still in contact with the ball all through here, right? Think of it. If the club wasn't in contact with the ball, how can there be a force on the ball? As soon as the ball isn't touching the club, there is no force on the ball. So the force does increase until it reaches a peak value, and then it decreases. But that's okay, because it's still a force. You think, oh, wait, this is This is reducing the impulse that it's going to impart to the ball. No, it's not. No, it's not. There's still a force, and the force, look, 2,000 newtons is better than 0 newtons, right? Not as good as 5,000, but it's better than 0. So the longer you can keep the force on there, even if it's a smaller value for force, the longer you can keep the force on there, the better. The golf club and the ball separate right here. So the impulse that we want is 2.5. If they separated right here, then we'd have to find the area of only half of the triangle. But that's not the case. Okay, does that make sense? There could conceivably be a question sometime where you do have to find the impulse of part of the problem. But normally they'll tell you that if that's the case. Okay, what's delta V going to be here? Somebody's going to calculate. You guys are all going to calculate that with your calculators, please. 54.5, so 55 meters per second. Okay. And it's to the east, right? Because that's the direction that the force is applied on. So from 0 to 55 meters per second in 1 second. Hey, if you don't believe me that this is still beneficial down here, even though the force is smaller, cut it off. Right, try a problem. Try a problem where you don't have the extra force, okay? And see what happens. All right. Got a couple questions for you to work on page 462. I'm going to ask you to take a stab at those now, okay? And take a walk around. Let me know if you have any trouble with it, okay? Let's have a peek at number 2 now. It says, 2A says, a soccer player heads the ball with an average net force of 21 newtons to the west for 0.12 seconds. Draw a graph of the average net force on the ball as a function of time and assume that F net is constant during the interaction. So we're going to draw, let's define west as positive, therefore everything can be above the x-axis. If we make east positive, then that's okay. It just goes below the x-axis instead. That's all. Not a big deal, right? Here's my force in newtons to the west. That's not northwest. That's newtons to the west. And then I've got my time here measured in seconds. It's an average net force of 21 newtons. I don't need to draw all the numbers up the side there. 21 newtons there for 0.12 seconds. Okay, that's good. Good enough. There's my graph. Now the question says, in B, says, calculate the impulse provided to the soccer ball. Now, there's a couple ways you can tackle this one. What's one of the ways that you could tackle this one? Once I got my graph drawn, everybody should think of 3 words, right? What are the 3 words, Tasia? Yeah. Good. Area equals impulse. We can find the area of this, right? Impulse, or the area, is equal to base times height. What's the base? 0.12 seconds. What's the height? 21 newtons, right? What does that work out to be, guys? Yep. 2 decimal. Okay, thank you. 2.52 Newton seconds. Anybody do it a different way? How'd you do it? Okay. Good, I'm glad you said that. Didn't I tell you guys when we were doing the example that you couldn't do F times T? I did, didn't I? Why can you do it here? Good. The value of F isn't changing. So it's okay to do that here. Okay. What's F? 21 newtons. What's time? 0.12 seconds. Now, my suggestion would be when you see that graph, still stick with area. But in the end, this gets you the right answer in this case because it is a nice flat straight line. Works out to be 2.52. Did you look at what I really did here when I found F times T? What's F? It's the height. What's T? It's the base. So didn't I really find the area when I multiplied F times T? Okay, as long as it's a straight, flat, horizontal line, then the area will be F times T. So it works out either case, either way. C, the impulse changes the velocity from 4 meters per second to 2 meters per second to the west. What's the mass of the ball? Well, look, we know the impulse. What's the impulse? 2.52, regardless of whether you found it your way or your way. Okay, the impulse is 2.52. Well, we want to find the mass. That's different. What's delta V? Yeah, VF minus VI. Now, the way that I've kind of set this up, you got to kind of be careful now, the way that I've set it up. I've made west positive, right? So this would be positive, this would be negative. I would say 2 minus negative 4. What does it give me? I mean, it works out the other way too, right? Because you just say 4 minus negative 2. Okay, if we, I'm just sorry, 2 minus negative 2 minus plus 4. We just get a negative 6 instead of a plus 6, that's all. 2.52 equals m times 6. M is equal to 2.52 divided by 6, which is, I don't know, somewhere in the range of 0.4 or something like that. Is that okay? Got a little side question about this question, okay? Soccer player heads the ball with an average force of 21 newtons. So what's the force on the ball? What's the force on the ball? Yep, 21 newtons. For how long? 0.12 seconds, right? What's the force on the soccer player's head? How much force is on the soccer player's head? 21 newtons. If object A applies the force on object B applies an equal and opposite force on object A. So if you apply a force of 21 newtons on the ball applies a force of 21 newtons on you. For how long? 0.12 seconds. Okay, so I apply a force of 21 on the ball for 0.12. The ball applies a force of 21 on my head for 0.12. If I give the ball 2.52 Newton seconds of impulse, then the ball gives my head 2.52 Newton seconds of impulse, right? Kind of like Newton's third law, right? Object A applies a force on B, B applies an equal and opposite force on A. Not only are the forces going to be the same, the impulses are going to be the same as well, but opposite direction. If this is 2.52 on the ball, on my head would be negative 2.52. That's all, right? Does that make sense, guys? All right, what I'd like you to take a look at now is worksheet number 2, please.